Hey, what's up, everybody? Here is a video on vertical circles. Uh, Very similar to horizontal circles, except you need to take into account the force of gravity and also the direction that we're going to call positive is going to be a little different than what we've done before. But we'll jump in and you'll see, and hopefully it won't be too bad for you. So one kind of thing to note, we were talking a whole bunch about G-forces in the last lesson. If you ever watch spacey movies with, I don't know, Ender's Game or something, where they've got areas where they've got gravity and areas where they don't have gravity. They actually just have simulated gravity, and the whole idea is based on, oh, I don't have a felt pen yet. The whole idea is based on these spaceships spinning around in circles. So that's kind of hard to see my felt pen on there, but spinning around in circles. And typically to simulate gravity, they have AC, so around the outside of the circle, they have AC equal to G. So in other words, their acceleration is equal to 1 G force. So if they are standing, let's see, standing on the outside of that circle and it is rotating around with an acceleration of 9.81 meters per second squared, this person would feel like they are here on Earth. So anyways, yeah, artificial gravities in movies and stuff like that, Interstellar, Ender's Game, all those different places where we have those giant spinning wheels. This is why we see those giant spinning wheels. Okay, so vertical circles. Bunch of different situations, like we can have part of a vertical circle. Well, we have a pendulum swimming. We can have a car going around the inside of a loop-de-loop. Golfer we don't really deal with very much, but we got to take into account a whole bunch of different things with these. One of the things we need to take into account is maximum or minimum tension. If you guys have something that you can swing around on your finger, that's awesome, like keys on a lanyard or something like that. Try and keep it as a constant speed. You might want to take a minute right now to spin it around and figure out, okay, well, where is the tension the most? Where's the tension the least? And the tension, remember, is going to be somewhat uniform throughout your keys. So as you're spinning it around, you should notice that the least amount of tension is at the top, so it's pulling on your fingers the least amount at the top, and the most amount is at the bottom. So let's see. At the bottom of the swing, and if we wanted to figure out why we have the maximum tension at the bottom of the swing, we have to keep in mind that this thing is moving around with uniform circular motion, which means the magnitude of AC is constant. Magnitude only. The direction, remember, keeps changing. And the velocity, or at least the speed, I guess I should say, is constant. The velocity is not, because it, again, keeps changing. So if I were going through and looking at this, and I was trying to think about the forces that are acting on this, the two forces that we have force of gravity moving downwards, and then I have the tension force moving upwards, and you can think about why that tension force would need to be upwards. Which way is the net force? Net force is always towards the center of the circle. So if I need my net force to be about this big, excuse me, if I need my net force to be about this big, it's very clear that the tension force has to be larger than the force of gravity in order to have some leftover net force. And remember, net force, F for circles, there we go, Fc is the net force for circles. So in other words, when you add up the tension force and the force of gravity, the tension force has to be bigger so that we've got some leftover force towards the center of the circle, some leftover net force. Cool, so that is at the bottom of the swing. If we picture the top of the swing, this is where we're going to have minimum tension. And the idea with this is we still need that net force, or that Fc, going down towards the circle. So in this case, gravity is actually helping us out. So you'll notice that Fc is only slightly bigger than gravity in this case, which means we need I should have drawn this off to the side, a fairly small tension force to make up for it. So in this case, Fc is going to be equal to Fg plus the tension force, and they're in the same direction. Everything is down, so we're going to call, in this case, down positive. And that's something we want to look at with both of these. So we'll go back to this one and we'll build a little bit of a formula. In this case, we're going to call up positive. Uh-oh, that whole thing just moved on me. There we go. So in this case, we're going to call up positive, and just generally, we want to call the center of the circle will be positive. So as I'm building this formula, we can say FC is going to be equal to our tension force, but again, for this bottom of the swing, maximum tension, tension force has to be bigger, plus the force of gravity, but we'll know that the force of gravity is negative. So one of the things that I actually do in this unit quite a bit is we go through and we say FC is equal to the tension force. Oh, and my felt pen is not working in this corner of the screen. Tension force minus my force of gravity. So again, rather than doing plus a negative, we just say minus. But yeah, this is our formula for our maximum tension, happens at the bottom of the swing. At the top of the swing, it's very, very similar, except again, we're going to call the center of the circle positive, so we're going to call down positive. And the reason for that is, well, look at everything. Like, I come over here, and I see everything over here. Everything is down, so there's no point in messing with that. Why would we include a bunch of negatives when we don't have to? Down is going to be positive. Whereas in this one, because we're going both in and out of the circle, up and down, one direction has to be positive, one direction has to be negative. And we're going to call the center of the circle positive, so up positive. Cool. So again, as a little bit of a review, our minimum tension happens at the top of the circle, our maximum tension happens at the bottom. And again, this is because both the weight, remember weight is force of gravity in physics, and tension are downwards, so they are both helping the centripetal force, or both contributing to the centripetal force, whereas the tension and the weight are working against each other at the bottom of the swing, and the tension has to overcome the work and also have some net force or centripetal force left over towards the center of the circle. So a couple of quick examples here. I got a 2.8 kilogram object attached to a massless rod, and it's spun in a vertical circle with a period of 0.72 seconds. Determine the tension the minimum tension is 20 newtons, determine the length. So as we go through, we've got things like mass, we've got the period, we know that it is the minimum tension, so I'm underlining that because it's actually really important as well. And I know that the whole thing as a minimum tension of 20 newtons. We're trying to determine the length. When we think about this length, so from here to here, and this thing's whipping around in a circle like this, how does length actually correspond to something that fits into our formulas? Well, hopefully you can see it. Length is the radius. So let's go ahead and let's start figuring this out. Minimum tension, where does minimum tension happen? Well, it happens at the top, so I'm going to draw myself a free body diagram with the ball happening right at the top. So it's swinging around in this direction. And then I know that I'm going to have force of gravity acting downwards. I know that I'm going to have my tension acting downwards. And I know that FC is also going to be downwards, which I'll kind of leave off to the side. If both the forces are downwards, obviously the net force is going to be downwards. So then once I build my formula for this, so FC is going to be equal to, and this is the difficult part, is always building your formula. It's going to be FG plus the tension force, there we go, FT. Can we figure out what FC actually is? Well, it's just M times G, plus we already know what the tension force is, so this is fairly straightforward, 9.81, use newtons per kilogram because we're dealing with forces, times the mass. What was the mass? 2.8 kilograms. Plus, this might get a little bit sloppy here, and also I don't have my calculator ready, so I better get going with that. Plus the tension force, we said the tension force was 20 newtons. So FC, or my net force for this circle, 9.81 times 2.8 plus 20, should be 47.468 newtons, and obviously that's downwards because literally everything is downwards. So now that I know FC, we could do this in a couple different ways. FC is equal to M times AC. So we could go ahead and solve for AC and then solve for the radius from there. Or we could just think to ourselves, I got AC is equal to V squared divided by R, which is also 4 pi squared R divided by T squared. So we're looking for radius. It's actually in both of versions of this, but because we're given period, we can plug this one in here. So this is going to be FC is going to be M times 4 pi squared times r divided by t squared. And we got a bit of a rearranging to do here, so let's just go ahead and take a look at that. Radius is going to be equal to fc times the period squared divided by 4 divided by pi squared and also divided by m. So take a minute, make sure you are good to go with that rearranging, and then all we got to do is plug in some numbers. So the radius is fc, we already found that, so 40, I hope we have enough space here, 47.468 newtons times the period. I think in the question it was 0.72 seconds, and then we got to remember to square that one, divided by 4 divided by pi squared, and also divided by the mass. What was the mass? 2.8 kilograms. So we end up with the radius being, hold on, I gotta plug this in here, 47.468 times point. You should be doing the same thing, by the way. Plugging in, make sure you're getting to the same place. Divided by 4 divided by pi squared. Don't forget to use the pi button. And then divided by 2.8. So I'm ending up with a radius of 0.2226 meters. Let's check out the SIGDIGs for this. Looks like 2 of them. So 0.22 meters or 22 centimeters if you want. So kind of reasonable for, you know, maybe a guy swinging his keys around or something like that. I don't know, 2.8 kilogram keys might be excessive. So anyways, yeah, hopefully you get the idea. If you really want to, you could cram this together in one gigantic step. So on the left-hand side of the board over here where we've got FC is equal to FG plus FT, you could expand on FC as well if you want to. I just find that a lot of people, well, they find that to be a bit much, right? So I typically find FC, and then, you know, you can substitute FC, or I should say AC with 4 pi squared r divided by t squared on the other side. Anyways, hopefully this makes sense for you. I feel like I'm rambling a little bit at the end, so let's move forward. Okay, so slightly nicer diagram than I've got. A little bit of space to work. Oh, look at that. I had it done for myself anyways. 22 centimeters. Okay, next thing we want to talk about is apparent weight, and we've kind of already talked about apparent weight, right? We talked about that in Unit 4. Apparent weight is also known as our normal force. It's Fn, it's how heavy you feel, and it's what would be measured on a weigh scale. It's often referred to as the g-force on an object, and remember we talked about g-force. It's actually easy to talk about accelerations than the forces, but it does work with forces as well. So anyways, normal force is apparent weight, and don't forget force of gravity is your actual weight, how much you actually, so how hard the Earth is actually pulling on you, or while gravity is actually pulling you, and normal force is just how hard it feels like you're being pushed in the ground. So then the next thing is, if you've ever been driving around or maybe skiing or something and you go down to the bottom of a dip, you'll notice that you feel way heavier at the bottom of the dip. And if we wanted to explain why you feel way heavier at the bottom of the dip, we can use our ideas of circular motion. So even though it's only part of a circle, it's still circular motion. So you're moving at a constant speed. We've got gravity pulling you downwards. What is pushing up on the ball? Well, in this case, it's actually the road that's pushing up on the ball, which means that's our normal force pushing up on the ball. And just like if we were whipping, you know, keys around in a circle, because we're at the bottom of the dip, this is going to be our maximum Fn, or maximum apparent weight, just like it was maximum tension with the keys. And if I were looking at this, we would call up positive. So as I'm building my formula, Fc is going to be equal to Fn minus Fg. And keep in mind that you could also do Fn plus negative Fg, would be essentially the same thing. So Fc is equal to, actually I should put brackets around the whole thing. That makes a little bit more sense. So anyways, at the bottom of the dip, hopefully you've noticed this, you get heavier. There's this one run at Sunshine Village, if anybody ever goes skiing, that you go down one side and then you go up the other side of a valley, and you can see so many people, I don't know how to draw a skier, just sort of like okay, some poles or something, they crash at the bottom of that hill because their apparent weight is so much more. They're not ready for it. Their legs just sort of give out on them. Maybe you felt that before. You're running down the bottom of a hill and then it flattens out. You feel way heavier at the bottom of the hill. I'll also show you a great video on this next lesson. But yeah, okay, so bottom of the hill. If we're looking at minimum normal force, so therefore minimum weight, that would happen at the top of the hill. Typically, you don't go around the inside of hills, like that's like a loop-to-loop or a roller coaster style thing. If you're driving your car, you typically go over the top of the hill. So this one gets a little bit, this is the one situation that's a little bit different. So force of gravity still acts downwards. That's fine. Which way is the net force? So if we're going around in a circle like this, the net force is always towards the center of the circle. So I'll put that as a dashed line. FC has to be downwards. And then which way is the hill pushing on the car? If you say upwards, you are correct. So our normal force has to be upwards in this case. Remember, we always wanted to call the center of the circle positive, so that means we're going to call down positive for this one. So as I build my formula, FC is going to be equal to Fg minus the normal force, or if you wanted to, I'll put this in brackets again, you could put Fc is equal to Fg plus negative normal force. So in this case, gravity is positive, and that just keeps Fc always, always, always positive. And we know that the normal force has to be smaller than the force of gravity so that there is some centripetal force left over acting downwards. So in other words, the down force needs to be bigger than the up force because the net force is downwards. So the up force being Fn, which is your apparent weight, is actually going to be smaller than your force of gravity. So your apparent weight is smaller than your actual weight. You are going to feel lighter than you actually are. Cool. So anyways, it's building a formula for that one. Here's a slightly better diagram on this one. I'll give you a second to read it. Since the object is going up the hill, it wishes to keep moving upwards due to inertia. This results in less pressure between the surfaces and thus less normal. Okay, so one thing with this is like, well, what if things are going really fast off the top of the hill? Well, they jump, and what would the normal force be if they're jumps or if they're in the air? Remember, Fn, so you're in free fall, so the only force acting on this is the force of gravity, which means Fn is equal to 0. So your apparent weight is 0 if you are flying through the air. The idea of this one is like you're going so fast that your inertia is carrying you up and off the hill. If the hill's not pushing on you, then you don't, well, this is going to sound redundant. You don't feel the hill pushing on you. You have 0 apparent weight. So again, rally cars in free fall are great examples of this. Driving a rally car would be pretty cool. Okay, so second example here. I got an 84 kilogram person inside of a 1200 kilogram car is sitting on a scale. So that is the 84 kilogram person that is sitting on the scale, not a car. Cars don't really sit on scales, at least not when they're moving. So if this person drives into the bottom of a dip with a radius of curvature of 15 meters at a constant speed of 91 kilometers per hour, which let's go ahead and do 91 divided by 3.6, 25.27778 meters per second. We want to determine the maximum scale reading, and we know that maximum scale reading happens at the bottom of the hill. So we could go ahead and we can make a little, free body diagram for this one. Force of gravity is going downwards. We know that our normal force has to be bigger and has to be upwards so that the net force, Fc, can also be upwards towards the center of the circle. So then we have to build our equation for this. So Fc, oh, and I forgot one little thing here. What are we going to call positive? Center of the circle is always positive, so in this case, up is positive. So Fc is going to be equal to Fn minus Fg. It's asking us for the scale reading, which gives us our normal force, which also gives us our apparent weight. So we have to rearrange and solve for normal force. So Fn is going to be equal to Fc plus Fg. And notice the direction is already built in, so I don't need to put direction in any of these numbers. I just need to expand a little bit. So Fc is going to be m times AC, and FG is going to be M times G. We can again take a little bit of a shortcut here, and we can say, so it's going into constant speed. So I'm going to use AC is equal to V squared divided by R, and I'm going to plug that into my formula over here. So my final version of this is mv squared divided by R is equal to m times, or not equals to, what is this? Plus m times g. So again, we plug in the numbers. We should figure out pretty straightforward what the normal force is. So it's an 84 kilogram person times the speed, which we figured out was, what is it, 25.27, 25.27 meters per second. We want to remember to square that, divided by the radius of curvature, which was 15 meters. And then we want to add to that m times g, so that is 84 kilograms times 9.81 newtons per kilogram. And that side of the smartboard is not working at all, so let's move this way up. Newtons per kilogram. And then all we have to do is, crunch some numbers here. So 84 times the answer squared divided by 15 is equal to plus 84 times 9.81. So this normal force on this person, 4,402 newtons with sig digs. Let's just go back up and check it out. So it looks like 3 sig digs all around. So let's change that to 4.40 kilonewtons. If you want a bit of a bonus question, you can figure out how many g-forces that is. I think it's going to be quite a few. It's a tight circle, and he's going pretty quick around it. But yeah, so this person, like if I did the 84 times 9.81, 84 times 9.81, their normal weight is 824 newtons, but they are feeling like they are 4,400 newtons. That is significantly heavier than they actually feel because they are at the bottom of the dip. Cool. So let's see what we got next. Oh yeah, maximum scale reading at the bottom. Man, I got all my stuff all figured out here for me already, which is kind of nice. The one thing that I do want to show you, last thing that I'll show you guys, is what if you're on the inside of a loop? So typically cars don't drive on the inside of a loop, but some fancy cars do, some roller coasters do. If we were building a formula for this, this one would also be minimum normal force. So minimum normal force, minimum weight is always at the top. But if I wanted to build my formula FC, what is it actually equal to? Well, first we'd say down is positive, and then I'd think to myself, oh, okay, well, force of gravity is always down, so that's fairly straightforward, that's normal. But which way is the track pushing on the car in this case? The track is actually pushing downwards, so our normal force is downwards, so FC is just going to be equal to FG plus Fn for this last one. Again, call down positive, everything is downwards, everything is positive. Okay, so that is pretty much the lesson. Make sure you practice, 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 work out all the kinks, and we will talk again soon. Bye for now.